Let me ask you a simple question, but the answer, well, it might make you a little uncomfortable. Can you really trust your computer?
I mean, really think about that. You hit the power button, you see your familiar desktop, you type in your password, everything looks normal. But how do you know? How can you be absolutely sure that somewhere deep in the code, a piece of malware hasn't dug itself in, just waiting for you to boot up? Well, the scary truth is, if you're only relying on software, you can't. You just can't be sure.
And you know, this isn't some new fear. This quote, yeah, it's from Hamlet, but it's used in our source material. It just perfectly captures that deep-seated unease that security experts have felt for decades about the whole state of personal computing.
So, let's dig into that. Before we can even talk about a solution, we have to really get our heads around the problem. Why are our computers so fundamentally untrustworthy to begin with?
Okay, so what do we even mean by trust here? Well, the official definition talks about a feeling of certainty. Certainty that the system will do what it's supposed to do and nothing else. But as we've already hinted, when you're talking about millions of lines of code, certainty is pretty hard to come by.
So our lack of certainty really boils down to three big problems. First up, something called mutability. It's just a fancy word that means pretty much any piece of software on your machine can be changed. Not just your data or your apps, but the really deep stuff, like device drivers, kernel components, even the BIOS, the very first thing that wakes your computer up. Second, we have a privilege problem. Most of us run our computers as administrators, which is basically like handing a master key to any program that asks for it. And finally, there's just the sheer scale of it all. There is so much code on a modern machine that it's literally impossible to check all of it.
So, if software is the problem, what's the solution? Well, way back in 1999, a group of companies got together and they landed on a pretty radical idea.
And this was the heart of it. They realized you cannot solve a software problem with more software. The whole foundation was shaky. The only way to build a system you could actually trust was to anchor it in something that couldn't be easily changed, something physical, something in hardware.
And this is it. This was their answer, the Trusted Platform Module, or TPM. It's just this small, quiet chip that sits on your motherboard, and it was designed to do just one thing: be that solid hardware-based foundation for trust.
And this picture really shows you the TPM isn't just a simple chip. It's basically a tiny, self-contained, tamper-resistant computer living inside your main computer. It's got its own processor, its own memory. It can even generate its own cryptographic keys. Think of it like a tiny, fortified vault built right into your machine.
Okay, but how does one little chip secure an entire, complex computer? Well, it can't do it alone. Instead, it kicks off this incredibly precise, carefully choreographed process every single time you hit the power button.
And it all starts with this concept of a root of trust. The TPM's whole job is to be that root of trust. It's kind of like the concrete foundation of a skyscraper. If that foundation is solid, if it's unchangeable, you can build everything else on top of it with confidence. The TPM is that solid hardware foundation.
So here's how that foundation gets used. It's a process called the chain of trust. First, our unchangeable hardware, the TPM, kicks things off. Its very first job is to take a cryptographic measurement of the BIOS. That's the first software that runs. This measurement is like a unique digital fingerprint. If even one bit of the BIOS has been tampered with, that fingerprint won't match. If it checks out, the BIOS is now trusted to do the exact same thing to the next piece in the chain, the operating system's kernel, the heart of Windows or Mac OS. And this process continues, each link in the chain verifying the next, until by the end, your entire system has been verified to be in a known, good state, all before you even get to the login screen.
Now, in theory, this sounds incredible, right? A computer that can literally check itself for tampering every single time it boots up. But, you know, the journey from a brilliant idea to a feature that everybody actually uses, well, that road can be pretty bumpy.
The promise here was just immense. With this trusted platform, you could do amazing things. You could seal encryption keys to the TPM so they would only be released if the system was in that known good state. You could prove to a corporate network that your computer wasn't infected before it was even allowed to connect. This stuff was supposed to solve some of the biggest headaches in cybersecurity.
And it wasn't just theory. It led to real-world features you probably use right now. Microsoft's BitLocker, the full disk encryption built into Windows, it uses the TPM to protect its encryption keys. This is that sealing idea in action. If a hacker messes with your boot process to try and steal your data, the TPM just refuses to release the key. Your drive stays a useless, encrypted brick to the bad guys.
But, and this is a really big but, here's where all the trouble started.
There's this fundamental tension at the very heart of the technology. See, a tool that can be used to make sure your computer is secure for you can also be used to make sure your computer is controlled by someone else. And this is the whole debate over digital rights management, or DRM. Could a company use this chip to stop you from playing a movie you own or copying a song you bought? And these fears, they created huge roadblocks. Adoption was incredibly slow. For years, almost every business laptop shipped with a TPM chip, but it was almost always turned off by default in the settings. The whole fight over DRM, plus a big philosophical clash with the open source community who, value user control above all else, it just meant that trusted computing never had that big revolution its creators were hoping for.
So, was it a failure? Did the whole thing just fizzle out? Not exactly. Its legacy is way more complicated, and honestly, a lot more interesting than that.
See, instead of a big, noisy revolution, trusted computing became a quiet evolution. It didn't take over the world overnight, but its core ideas slowly but surely got baked right into the foundations of our modern operating systems and security.
And that brings us right up to today. The idea of a hardware root of trust, it's everywhere now. You see it at Apple's Secure Enclave and their T2 security chip. They do a lot of the same things. You see it in that controversial requirement to have a TPM 2.0 chip just to run Windows 11. That tells you that Microsoft now sees this as a non-negotiable part of security. The original dream of trust anchored in hardware isn't some niche idea anymore. It's basically the price of admission for modern computing.
So, we kind of end where we began, but with a new question. The tech to build a truly trustworthy computer. It exists, and we're using it more every single day. But as it gets deeper into our systems, that central conflict, that tension, it's still there. To get total security for ourselves, how much control over our own devices are we willing to give up? That's a question we're all going to have to answer.